Right. Yeah. And good morning and good afternoon and good evening, everyone. And I hope you all can see my screen and I'm audible to all of you. And we are, as you are aware, repeating the series 1 on plastic flame retardancy. It was really heartening to see a lot of queries and the interest for the repeat of this, not the video, because they want to go through the process and understand and even ask more questions than what was communicated in the first series. So we are very glad to bring it to you, the series 1 again. And as explained earlier, this is for practicing professionals so they can understand it better, because the what we are going to present today will be associated with the electrical electronic industry, and it will be the design, selection, processing, testing, and application of flame retardancy of thermoplastics. And each webinar, as you have gone through, will be 45 minutes, and 40 minutes will be presentation and 5 minutes will be question answer session. And I request you all to put your questions in question answer box, and we will be answering at the end of the session. And as I mentioned earlier, it is more towards practical than theory based. So the people who are practicing and using these FR grade materials in day-to-day activities, they can appreciate better about what we are going to present today. So it is the topic we are going to cover today is history, need, and ISO classification, and FR chemistry of plastics. And since we are repeating, and from now on we are not, we are having a very cluttered schedule, and we have to go through this one by one without any further delay. So this is the plan we have for the other series. Series 2 is scheduled on 20th August. Series 3 will be 31st August. And from there onwards, we are planning to have 2 each every month. And in series 13, which is on 2021, from there we will be taking the presentations will be based on your interest. So we welcome everyone to contribute with your interest. So based on the interested topics, we will take the webinar topics forward. And we have some of the industry professionals who are going to present our upcoming seminars. And for this, the plan is to have more webinars. We invite the industry experts and professionals to come forward and present the future webinars. And as you are aware, Eurostar Europe and the FPL Asia, we are specialists in engineering polymers. And so the examples will be mainly from polyamide, ABS, and PP. To one of the speakers today, Mr. Sekar, is a science graduate specialized in polymer engineering with his master's in business administration. He have over 36 years of experience in formulation, compounding, and application development. After working for others for a few years, he started his venture in 1991, co-founded his venture, and he is the immediate past chairman of Governing Council of Indian Plastics Institute, a professional body with more than 3,000 members, of plastic engineers and professionals. He current governing council member of Plast India Foundation, an apex body of all major plastic associations in India, and he's the past president of Tamil Nadu Plastic Manufacturers Association (TAPMA), and the past governing council member of CIPET. He also sits on the board of many universities which are teaching running polymer courses. He will be covering history and need of FR in today's series. And our second speaker today is Mr. Alexis Chopin. He got his master's in engineering degree in polymer engineering. I have over 25 years in formulation, compounding, and application development. His functional experience is very much linked to today's topic, and he is linked to development of new material and electrical electronic segment, polyamide, flame retardancy, which we are going to talk about today. And he is a co-applicant of many patents and co-author of many papers in relation to FR engineering, plastics, and compounds. He's a subject matter specialist in LV and MV control FR design section. He will handle ISO classification, FR chemistry, merits and demerits today. And with that, I handed this over to Mr. Sekar.
Thank you, Balakrishnan, and good morning, good afternoon, good evening to all the participants from Europe, Middle East, and from Asia. And I hope I have the permission to share the screen. And that screen is visible?
Yes, it is visible. Maybe it has to be full screen.
Okay.
Yes.
Okay. I have a much easier subject to talk about history and of flame retardancy. And let me straight away get into the thing because Alexis has got more to say. Let me not take much of his time. I'm sure.
Before we go, it is not in full screen. Could you please do it so everyone can appreciate?
I made it as a full screen.
Oh, in our screen it looks smaller. Maybe we have to stop the screen share and start it again.
I don't know. I think every webinar we get stuck on something always. And the new share is available. Can you disconnect me and then connect me? I mean, the sense that remove my authorization of sharing and then.
I will.
No, 1 minute. I'll try. 1 minute. 1 minute. Don't try. Is that getting into full screen?
No. Yeah.
Is it full screen now?
No, it is not full screen.
I don't know whether you have technical problem or what about Alexis? You are able to see it as a full screen?
No, I see you on a small screen too. I don't know why.
Maybe you have to allow enable editing and.
Okay, I will stop here and you can share my screen. Okay. I will ask you to run that.
Okay.
And as Balakrishnan is preparing to share, let us, yeah, you can get into the next slide, please. If you all know that history of plastic is about 100 years now, 110 years of plastic history is there. It got first invented in 1907 with a bakelite. I'm sure all of you are familiar with the telephone which is shown at the bottom and the round bakelite switch. I'm sure even in villages you will be able to see them even today. That's okay. I will finish it off in time. Don't worry. Okay. So thereafter the PVC got invented in 1913, and of course nylon got invented in 1935. Carothers in US invented polyamide. And of course, Second World War is a turning point, and after that, a few more polymer got invented, like ABS in 1948, and polypropylene in 1952. Polycarbonate got invented in as late as 1958, etc. So till the time it was used in packaging, I think you can see, I think 1950 it was only 0.5 million tons globally consumption. And 1964, it got into 15 million tons. And today, I would say 2 years ago, it was around 320 million tons. So you can see the kind of growth which has happened. But even though the growth has happened in multiple things, the polymer inventions were not really happening. Linear low density polyethylene, polyethylene which is made into linear low density, a slight modification in LDPE. But the most of the work which was done is primarily on compounding and extending the polymer into newer applications. Okay, let's go to the next slide. So there are many applications. I think today plastic is there in everything, whether it is automotive, electrical, packaging, infrastructure, defense, aerospace, industrial, you name it. I think plastic is there in almost all the points. And since we are talking about flame retardant, I think if you look at this slide, I think you can see that in automotive today, most of the underbonnets are becoming flame retardant because of the fire accident which has happened in the vehicles. And with the electrical vehicles coming in, I think more and more flame retardants are different polymers are getting in. And electrical and electronics, large extent wherever current carrying parts are there, it has been flame retardant. And complete transport industry, whether it is train transport or it is aerospace transport, all of them, all the parts are flame retardant because we don't want it to catch fire in case of accident. So the flame retardant is also becoming a very substantial part of business. Okay, so next slide. So this is about India, and even though there are many people attending from neighboring countries and as far as Middle East and Europe, still most of them are from India. I think almost I could say 60-70% or 60-70% of the people are from India. So it will be relevant to say in India, yes, polymer got started from the year 1957 onwards with a very small volume. And you can see the graph below, which say that in 1990, we were only about 980 kilotons. And today we are about 1,800 kilotons. So that means that we have grown substantially. And our per capita, for example, in India is around, it was around 0.5 kilos. That is half a kg per person per year. And it got improved to 13 kilos now in last 10 years. Whereas we are still far below the world average of 45, and leading countries like America, which is 110 kilos, Germans around 95 kilos and all that. Even China, as populated as India, is around 45 kilos. So there are a lot of scope for plastics to grow in where populations are there, like India, Indonesia, etc. Next. And let me not get into the history of polymers because plastics, I think, cannot be relevant to this series that we are talking. So we are talking about electric plastics in electrical and electronic industry, appliances industry, and electric vehicles in automotive. So most of this 10-12 series that we have planned, all of them will be covering about applications around this industry. Okay, let me make one thing very clear before we start this series itself. Is the goal of flame retardant is to inhibit or retard the ignition. There are some misunderstanding in the industry that flame retardant means it will not catch fire. It is not so. It will catch fire because after all, the polymer is organic material, which is a fuel. So it will catch fire, but the job of flame retardant is to put it off at the earliest. How quickly it puts off, without fumes, without a smoke. Those are all the areas where flame retardant has grown over the years. So if you look at the history in 1950s till 1950s, natural thermoset was primarily used in electrical and where current carrying parts were there. They behaved like metal, so people liked it because we were very familiar with metal that time. So we thought, yeah, thermoset which is behaving like the metal was good. There are a lot of limitations. I'm sure those who have worked with thermoset will understand that it is very difficult to produce, very slow process, productivity is very low, and flexibility is not there in the product. So there are a lot of limitations to the product. And between 50s and 65s, I would say that the first known material for electrical industry is PVC. And PVC, even today in cable industry, it is a very dominant user as for insulation. And PVC contains about, say, 60% approximately, I would say, 60% of its weight by chlorine. So the chlorine prevents oxygen to enter and damage the molecule, so it doesn't catch fire. So initially we were very comfortable with PVC, even though it had low insulation values, etc. But that was the first flame retardant polymer that we came to know to use then. Between 65 to 80s, there were a lot of natural flame retardants. That when I say natural flame retardant, a polymer by itself doesn't support flame. And they were something like polycarbonate, polyamide, PTFE. These are all the one which doesn't support flame by itself. So they were natural choice for industry, electrical industries or electronic industries where they want a flame retardant system. Okay. After 85, I would say that there are a lot of changes happened in modifying the material. People start modifying it with flame retardants like halogen based, because we learned that naturally that PVC, because of its high chlorine content, doesn't catch as fire. So we thought we will add a chlorine or a halogen to your polymer to make it flame retardant. Then we had metal oxide. Maybe Alexis will cover in a subject as to why metal oxides are used, because they generate water. And after all, we know water is a very natural way to put off flame by removing the heat. Then we had phosphorus, and there are many modern flame retardant systems are there. Next. And why this flame retardant requirements? I think when people start using plastics in electrical industries, especially for household appliances, there were a lot of fire accidents which were zeroed down to the plastic catching fire and propagating the fire. And I'm sure some of the movies we have also seen of large fires happening in trains or in long, tall buildings. And all that was zeroed down in those days in 60s to the plastic causing the fire. And of course, there is another drive happening in the industry is miniaturization. Now, everything is getting smaller and smaller and smaller in electronics. As it is getting smaller and smaller, the heat generation inside is getting increased multifold. So that is making the plastic to catch fire. And interestingly, I put that box here. It seems that we know flame retardancy, this human being knows flame retardancy as back as 450 BC. And people have soaked wood, Egyptians have soaked the wood in potassium aluminum sulfate, which is alum. And then it doesn't burn rapidly, the smoke is much controlled. So we know that how to control them, and that is what today we are using it. Next. Okay, so the initial days to catch a fire history, we know atmosphere that where we live, 21% is oxygen, and the balance majority is nitrogen, and 1% is carbon monoxide, carbon dioxide, hydrogen, etc. So people thought that this 21% is the cutoff for flame retardancy. So there were some polymer which are below 21%. For example, it is shown in the table: polypropylene, polyethylene, polystyrene, PPMMA. their oxygen index, limited oxygen index is 18. That means what does it mean is it requires 18% of oxygen in the atmosphere to catch fire. And whereas our atmosphere is 21%, so they burn very well. ABS is 19% and PBT is 20%. So there was some natural polymer, which I said, which doesn't catch fire. For example, polyamide, which is 24%. So it requires 24% of oxygen to catch fire. Okay, so whereas we have only 21% in the atmosphere, so it doesn't support the flame. Polycarbonate 27, and to know the strength of PVC, I'm just showing the number, which is 42. And PTFE, I'm sure all of you are aware that in our frying pan and other things, we are coating with poly PTFE today, which has got 95% oxygen requirement to catch fire. So initial days, oxygen index was the thumb rule of deciding whether the polymer is burning or not burning. Okay. And of course, on the left, on the other side, we have shown the pyramid of polymers, commodity and engineering polymers, then high performance engineering polymers. I think mostly all this series we'll be talking, as Balakrishan introduced. We are all people from engineering polymers, so our examples will be mostly on engineering polymers and high performance polymers. Whether it is amorphous or crystalline, there are different polymers are available. I'm sure all of you are aware, and they require a different chemistry to make it flame retardant. Next. So even self-extinguishing material, for example, polyamide, I said they've got an oxygen index of 24%. It doesn't catch fire. Okay, it doesn't catch fire, but what happens is when you want to make it as a color, okay, or rather, it doesn't. I won't say it will not catch fire. It is put off by itself. Self-extinguishing it will do. But when you do a color, when you add a glass fiber, when you add some mineral to control the dimensions, okay, then they are no more flame retardant. They don't. Their oxygen index drops. They start supporting the flame, and because of the reinforcement, compounding job done, some fuel has been added to the product, like lubricants, mold release, etc. So all this enables the flame to go up. So a compounding is required carefully to make a product of flame retardancy. Today you can make any kind of flame retardant, okay, in the sense that you can write all your boundaries. If you know to write a boundary that I want so much of insulation, so much of comparative cracking index, I want so much of dielectric strength, then we can make a product, okay? And of course, when you write the line that we want so much of cost, maybe there will be a challenge in that, okay, in reaching out the cost, okay? So it is possible to make by compounding process. The objective that we achieve in compounding process is to make it flame retardant. That is the polymer, which is a fuel, we try to protect the fuel. And we slow down the polymer burning so that the gases which comes out is slow. So it doesn't support the flame, and we reduce the smoke emission because one of the demand is smoke, because more than the accident, the people die because of the smoke which is generated, which is toxic and all that. So there are a lot of regulations today that what kind of smoke can be there, how long it will take to generate a smoke, etc., smoke density, etc. Maybe all that we will be covering in the series. And of course, there should be a polymer, you know, that when it catches fire, it starts dripping, you know, because it doesn't have the strength. So it drips. It drips with the flame, so it can catch potentially other parts nearby. So the damages could be much bigger. So the idea of flame retardant is to reduce the flame, reduce the smoke, give a more escape time, and slow down the gas formation and avoid dripping. Okay, so next. So there are a lot of environmental standards are happening. I'm catching from history to future. I think even today, a lot of environmental standards are there on the subject, which I already said, like smoke generation and toxicity of the material, etc., which is reducing the choices of flame retardancy. And of course, there are three things which are required. Alexis will be covering it in, I think, fuel, heat, and oxygen. Fuel is polymer. Oxygen, which is there in the atmosphere, heat is the outsource, which is causing the heat. So all this is making the combination of this is making the flame. So we can cut off any one to stop. We can control all the three to stop, reduce the speed. That is, we can reduce the heat, we can remove the oxygen, we can protect the fuel so that it doesn't burn. Okay, so this is about flame retardancy. And of course, the demand now is that industrial revolution, miniaturization, etc., triggering it, and electrification of auto industry. There's a big potential for flame retardant plastics, and increasing potential of fire hazard. A lot of standards are coming up. A lot of stringent requirements are there on safeties of human, which are associated with the parts. And of course, there are a lot of standards on safeties are evolving all around, and that is why the flame retardant technologies keep improving and marching forward. Next. Okay, with this, I will hand over to Alexis from Europe to handle the balance about ISO classification. The objective of ISO classification is when you see a flame retardant, you will understand by looking at the ISO number what flame retardancy has been used in the product and what chemistry, what merit demerits. Over to Alexis.
I don't know if you can hear me.
Yeah, very well.
Okay. So first, thanks so much explaining that today we are not talking about flame proofing, but flame retardancy, because it changes the life. And yeah, sometimes there is some misunderstanding. And it's really about flame retardancy. And what really are the motivation to flame retard plastics is, of course, to save life. This is the main topic. But the second one, which is, of course, of utmost importance for our customers, is to comply with regulations. Because more of the time, regulations are very stringent and they are very different from a business to another. You talked about electrical vehicle, where, let's say, standards are nesting or being written now. We are talking about, for example, low tension, or in MCBs, for example, where standards do exist for so many times and are very well known. So I don't know if you can see my screen. Yes, it's okay. Can you see my screen? Can you hear me?
We are able to hear you. Yeah, I don't know whether this is your screen or Balakrishnan is sharing his screen.
I'm still sharing the screen. You can share yours now.
I can share, yes, but I still, just like Mr. Sekar, I see my PowerPoint, but I cannot see.
The bottom you can say.
Or maybe you can flip the page like you did before. No, it's not mine because I cannot share. Last time I could, but this time I cannot share. I don't know why.
Just a second, I'll share it.
Yeah. If I have something special to do, just tell me.
So you can see the screen.
I have a very small vignette, a very small picture, but I don't know how to enlarge it. I will try to.
You can see the screen now. I'm
very small, but okay. I have duplicate mine, so I can. When you change the screen, I will be able to see. So let's say. Why it is so important to flame retard plastics? Because fire is a very harmful thing. You know, fire is toxic. You know, fire is toxic because it emitted fumes, and which is cause more casualty than direct fire. Fire is blinding. Maybe you cannot escape somewhere when there is a fire in your room, and fire is tremendously quick. Meaning that the fireman says that to extinguish a fire, you need, for the first minute of fire, you need 1 glass of water. For the second minute, you need 1 bucket of water. And for the third minute, 1 tank of water. And this is why a flame retardant can act. And fire is tremendously devastating because cost for insurance and cost in life is huge. So on this chart, you will see on the left side, but without flame retardant, the escape time in a room is very teeny, it's 2 minutes. whereas when the material is flame retardant, you have almost 20 minutes. And this makes a huge difference, because this is the best case when you can see the fire. But just try to imagine your part, for example, an MCB in an electrical cabinet. The fire can be nesting for some time, and it can propagate very quickly. So this is the way flame retardant act, and this is the motivation of using flame retardant, is or to prevent the fire from occurring, and this time we'll talk about ignitability of plastics, or to stop the fire, and then we'll talk about the flame retardancy of plastics. And the second chart shows you, for example, with the flash over time, which is the maximum energy the fire is releasing, can be really offset when you use a flame retardant. And this is very well in use, for example, for people in transportation, when they need to comply with regulation, where this time to ignition are of the utmost importance. So maybe on next slide. I don't know if it's, yeah, here we are. So on this one, we won't go into details. It's just to explain you, let's say, the type of flame retardant. We will go a bit more into detail into this presentation, and in the next webinar, we will go far more into details. What is important to understand at this stage is that flame retarding plastics is not just like coloring plastics. It means that to color plastic, you just add a few percent of some pigments, some dyes, and there you are. It does not change so much the properties of your plastics. But when you're talking about flame retardant plastics, you are talking about complying with regulation, and we are talking about reaching a certain level of flame retardancy. And it changed our life, because from time to time, you just need a few percent of flame retardant. But sometimes, for example, for transportation or for tunnels, you need to add more than 50% flame retardant in your plastics, meaning that it changes completely the behavior of a plastic, the properties of your plastics. So plastics can be used as an additive, meaning not just a pigment, meaning something that just only disperses into the plastics, but is not linked to the backbone, to the bone of your molecule. So this is about additive flame retardant. And to be honest, this is the more in use, especially in our world of engineering plastics, polypropylene, polyamide, and PVT. Reactive plastics is something which is a bit different. It is linked to the structure of a polymer and intimacy, I don't know the word in English, but so much linked that it cannot migrate. It's more the case when you are using, let's say, amorphous polymers. We don't have so many. What needs to be understood, it's a pity that I cannot share the mouse, but you see this round cycle, what is called the combustion cycle. Most of the time we hear about triangle of fire. And for a fire to occur, you need three different things. You need oxygen, you need fuel, and you need heat. And our action into formulating flame retardant plastics is to try to act on one of those three factors. And this is what we will see, let's say, in the next page. So I'm scrolling down. Yes. On this page, what is important is the diagram which you have on the top, when you see the polymer, the air, meaning the gas phase. So this is how we will act on the triangle of fire. Or we work on the polymer itself by shielding the polymer to the oxygen or the heat, meaning or you have to insulate physically the polymer from the heat, or you will act in the gas phase. In this case, you say you are poisoning the flame, meaning that you are consuming all the oxygen in the nearby of the flame to stop the fire, or you are adding to the heat by releasing something that will cool down the heat. So this is basically why you have three main effects. The first one is endothermic effect. So this one is just about cooling down the plastics, cooling down the flame, and diluting the gases. And it's more about inorganic metal oxide or nitrogen compounds. So the best example is magnesium hydroxide in polyamide. In this case, there will be different effects. We will see just in the page later. But this is really about thermal management. Radical quenching is another thing. Radical quenching, we will act in the gas phase, and it's mainly the case of halogenated compounds, where you will create organic species that will complex in the fumes, in the gas, and that will trap all oxygen available, so it cannot be present at the interface of the material and the air, so it will stop burning. And you have thermal shielding. Thermal shielding is typically the case for phosphorus compound. It can be organic phosphorus or it can be red phosphorus. In this case, you are just creating a char on the surface on the polymer, and you are physically insulating the fuel from the oxygen. So you will almost stop the fire. So action of flame retardant can be inhibition, can be dilution, char forming, removal of heat, and smoke suppressant. Because as I mentioned previously, smoke in most of the time is at least as important as fire, because an open fire you can control it. But fume can be toxic, can be blinding, and it really is the main problem, not to comply with regulation, unless regulation for transportation. But this is what is more feared by firemen. Firemen are more feared about the fumes and the smoke than the fire, because fire you can control it. Fumes you cannot do something, unless you, of course, you are very well equipped. So performance linked more to the material is polymer ignitability. So it's linked to a test that we will see later, not in this seminar, but in the next seminar. It's the ignition temperature of plastics, which is very different to flame retardancy. The rate of flame spread is very important for car industry. The heat of release is very important, for example, for trains industry. Formation of smoke and toxic gases are of importance for everybody, for every application which is unattended. In the UL standard, they call it unattended device, because basically, if this device can catch fire, maybe you are not there in the room, or maybe it's under the cabinet, it's nesting, and it will be very hard. And corrosive acid gases are very important for people who are dealing with telecommunication, for example, because you have to know that for example, in a telecommunication terminal, fire is not so more feared, because when it's on fire, then the terminal is not working anymore. But it's not so more important. But if a terminal is burning, then you can corrode all the contacts and ruin communication kilometers around, because fumes, corrosive fumes, can get into the pipes from a terminal to another, and economically it's a disaster. So on next page, we will see how for you as a user, as a customer, as an EOM, can see what's in your product and try to understand better what we are talking about. And for this, we will support around the ISO standard, which is the ISO 10043, and which is about flame retardant. So on next page, we can see how it is built. So next page, Bala. You see on this one, this is an example. The example you see is a polypropylene, GF30, it's about the filler, it's 30% glass fiber. Then you have PELO, so it's a plasticized with epoxidized oil, and you have FR52. And this is important, because in this case, you can see that the flame retardant used is red phosphorus. So I go quick because time is really flying by. So on next pages, two examples. Polyethylene, this one is PELD FR3040. So it's a polyethylene, low density, and it's a flame retardant nitrogen compound with organophosphorus. On example 2, it's a nylon 6 impact modified GF40 and flame retardant with red phosphorus. So on next page, we will scroll very rapidly the flame retardant system in use. But I think it will be more covered in a next webinar where we'll go more into details. But basically, you have halogen-based flame retardant system. This is the oldest one. This is, let's say, a very efficient one. As advantages or merits, these are very efficient. These are very stable. Stable to normal, let's say, nylon 6/6. Above for PPAs, it's a bit borderline. These are very stable systems. The drawbacks, the demerits, these are quite heavy, meaning that the price per liter for part is quite important. More important now is that it's recognized as it could be a toxic material. Not for every brominated flame retardant, but some of them are indeed toxic, and some of them are really not well perceived by non-governmental organizations. And people are mixing every, let's say, halogen system in the same one. So you have some that are really harmful that has been banned. You have other one that can be used for some times, and you have other one that are still of interest. This is why it's important to understand. Another drawback will be the limited tracking resistance. If you are in electrical application, for example, it cannot be too close to the arc. And in some cases, it can be corrosive. And this is especially when it burns, it can release bromic acid, which is very corrosive to metals and to connection for communication media. It works only with antimony trioxide, and this antimony trioxide in many countries now is perceived as a material to be phased out. Recycling is a challenge, especially in Europe. We know when we sorted all the waste, and reusing the waste now is a problem because we cannot dilute this halogen flame retardant system in all new materials. Next pages, we are talking about nitrogen flame retardant system. So this one is let's say, it's been the first step out of brominated systems. So it's a very efficient one. So for example, if we are talking about today FR30, which is mainly a melamine cyanurate, it's a very efficient flame retardant system, especially for polyamide 6. All the business for microcircuit breaker, MCB, MCCB in Europe went from brominated to halogen-free because of economical reason mainly. This is a very efficient and economic material, but there are some drawbacks. You cannot make a V0 halogen-free with melamine cyanurate. You are stuck to a V2 material passing the glow wire flame retardant system, but still in compliance with UL 746C that we will see in the next webinar. So it can be used, and it's more and more in use, and it's replacing in Europe brominated systems most of the time now. So I go very fast because time is really flying by. But next pages, we are about metal oxide system. So in polyethylenes or polyolefins, it's about ATH, aluminium trihydrides. So it's a molecule of aluminium, let's say, bonded with water. And when you heat the water, the plastics, water is released. Of course, aluminium trihydride is not stable enough for polyamide. For polyamide, we're using mainly magnesium trihydrates. It's the same thing. You know, you have a molecule of magnesium, which is linked with 3 molecules of water. And we are overheating this material. You are releasing some linked water. So water has different action. It dilutes the gases. It cools down the polymer. And from my side, it's a very, very nice material because when you are burning such a material, you are releasing only water vapor and CO2. So it's a more environmental friendly material. So we are working on it a lot. People are working on it a lot. It's very good for example, limited oxygen index. For example, people in trains or in tunnels can use them under the tunnels with a more stringent regulation, but there are some drawbacks still. You need a very high amount of flame retardant. So it's mainly in the range of 40 to 50%. So it has an impact on properties, and it has also an impact on price per liter. So it's a very interesting material, but for the moment is broadly major. We are selling in some application with very stringent requirements, but I think in 10 years, maybe it will be the flame retardant that people will be using. Next page is on phosphorus-based flame retardant. So we have mainly two types on this one. We have organic phosphorus, which can be used to flame retard V0 material, for example, nylon 666 with glass fiber. So with FPL, we are very unique, having material that formulation, let's say, with nylon 66 with 45% glass, V0 down to very low thickness, for example, and 5VA with a full RTI listing. So this is a very, very nice product, a high-end product. Let's say, on the other hand, we have also a formulation with inorganic phosphorus, and mainly we are talking about red phosphorus, which is still a very active material and a very, let's say, efficient material, because in this one you can have very nice properties with glass fiber and get a V0 material with almost the properties of a non-flame retardant material. So a lot of advantages. Some drawbacks is the color. It can only be black. And in some cases, let's say, if it's not well used, let's say, and especially if the material is not used very dry, you can have some phosphine concerns. So on next page, you have now some borate or silica system. This one are not so much in use in our business, let's say, of engineering plastics, but are not to be overlooked, especially for synergists. For example, zinc borate is a very efficient synergist that can replace, for example, antimony trioxide when you are looking for high electrical properties material. So this material are really in use. Next page is a kind of summary of what we can find. So this page is very true for, let's say, polyamide compounds. And I think we are very proud in Eurostar and FPL of being one of the very few companies in the world that can still offer almost the whole range of flame retardant that you can find. Because I like this chart. We should spend a lot of time. We won't today because we don't have the time. But mainly is to explain that there is no perfect flame retardant system. It's always a matter of compromise. It can be a compromise, of course, for cost, but most of the time it can be a compromise for performance. And what is true in a business, for example, an electrical vehicle, will not be true if you are making a contactor, if you are making an MCB, or if you are doing some train seats. Because you don't have basically, the goal is always the same, is to stop the fire or to prevent the fire from occurring. But if you are doing electrical stuff, for example, you will be very interested in tracking index, in electrical properties. So you will not be able to use some of flame retardant. If you are doing some business in transportation, for example, then you will be more concerned about smoke and fumes, and you really don't care about electrical properties. So there is no perfect system, but with all the range we can work in our company, we always can find, let's say, the best compromise. And let's say by having kept the possibility to work on all the range of flame retardant system, we always have something to propose. But we could spend hours on this one. It's not the topic today, but let's say the good thing, and I think it will be the topic of the next webinar to go more into detail about what compromise to be made and what we can expect from each flame retardant system. But yeah, this one is a kind of good summary of what can be found. But we are now at a level where we can propose some material at a V0 down to 0.8 millimeter, sometimes 0.4 millimeter, so very low thickness. We can comply with 5EA, with continuous in use temperature of 140 degrees C. So we can really offer a full range of flame retardant based on different technology. Okay, on next slide, it's just a kind of a resume of, let's say, the codes that has been explained previously. So there is a chart on the internet that you can find. And just to conclude on this one, things will change because non-governmental organizations are now taking a lot of care about toxicity of a flame retardant. And what was true yesterday or before yesterday is not true today, and will not be true tomorrow. So I think things will change, but if we have the basic knowledge of what is flame retardancy and how they act, I think we are toxic gases because you stop the fire, you prevent the fire from spreading outside, you save life. You know, so for me, the answer would be flame retardant material is very safe in use at molders, at users, and flame retardant material saves lives, really saves lives, and saves money, and this is a very good thing. You know, sometimes we have a non-governmental organization saying, yes, you should not use flame retardant material because you are using chemical. Yes, it's true, we are using chemical, but it's to protect. And if you are not using most flame retardant material, then the failure and the effect of a fire will be far more important than the risk which is taken by using those materials.
Thank you, Alexis. Next question is also from Nazimul Hassan. How we will set flammability rating for products? Anyone can answer.
I don't know how to answer that because it depends. Each product has got its own classification, its own standards, because it depends on the configuration of the part and the thickness of the part, etc. And there are different standards available for each of the part. So it may be difficult to answer a common answer to a very vast question. There is one more question on the chat box, I think from Flexicore India. To all the panelists, the nature of polyamide 6 is flame retardant naturally, as said. But why is it separately classified as PA as a compound and FRPA as a FR compound? Please explain the difference. I think I answered it in my presentation that yes, you are right, polyamide is self-extinguishing material at about 3 mm thicknesses. But once you make it into a glass reinforcement for better strength, better dimension stability, then it loses its flame retardancy. Then you have to add a flame retardant to make it as a non-burning material. And I hope I answered you.
Thank you, Mr. Sekar. And another question from Anil. Is there self-flame retardant resin without additives?
In a way, yes. In a way, yes. I think self-flame retardant materials, I think in one of the slides of Alexis was showing that it is possible to make a polymer also to have a flame retardancy. For example, PTFE. It is by itself is a flame retardant, or you can take, for example, a PVC without any plasticizer, without anything. It is a good flame retardant. Yes, it is possible, but there are a lot of limitations. That's why you have to add an additive and go ahead. I hope I answered, Mr. Anil.
Thank you. And another question from Sanjeev Kumar. What's the chances of getting ROHS2 implementation? Okay. I don't understand what he's trying to ask. Implementation date. What is the chances of getting ROHS2 implementation date? So,
from my side, I think ROHS is a kind of regulation of hazardous substance. So it's very well positioned in, and we know if the material we are delivering is ROHS compliant or not. ROHS is just a matter of a few elements. And it is something which is very easy to measure. It's mainly about lead, mercury, antimony, and things like this. So we can measure. So there are some formulations that are compliant with ROHS. Some are not. But yes, we have solutions that we can fully be compliant with ROHS and reach in Europe. It's no problem.
Thank you, Alexis. Mohan Gaikwad. Can we mold electrical parts, polyamide glass filled in 0.4 mm thickness? That is his question.
Depends on the application, but yes, for example, for terminal blocks, we have a material at FPL and Eurostar, which is listed V0 down to 0.4 millimeter. So then it's a physical limitation of a machine and the mold. The mold has to be designed, but molding 0.4 millimeter, this is something they know how to do in terminal blocks. Yes.
Thank you. So as we are very short of time, I take the final question. So FR-V0 is better than GWFI 960?
Oh, for me, it's very different. It's meaning that you have some material that can pass GWFI and that does not pass V0, and some which is the reverse side. But it's mainly linked to regulation and to different, let's say, philosophy. I think in US, for example, everybody wants V0. But in Europe, for example, which is more based on a EIC regulation, people would rather have a 960 glow wire than V0. Yeah, it's different by pole, but it's not equivalent for sure.
Thank you, Alexis. So, and that's the end of the question and answer session. And we go back to the slides. Hope everyone can see this. And as I explained in the beginning of the session, series 2 will be covering flame retardant mechanism and its selection criteria. And Dr. Rashmi Bharadwaj will be joining Alexis to present this topic. It will be on 20th August at 1500 hours Indian Standard Time. And if you have any feedback and more questions, as we couldn't include many questions asked in this session, please write to our email ID, and you can WhatsApp us on the given number. And you want to know more about both the companies and their products, you visit our websites, formulatedpolymers.com and eurostar-ep.com. And I thank everyone for joining in, and we appreciate your support, and hope you can take something away from this webinar today. And I thank all the panelists for taking your time, and thank you so much.
Okay, thank you very much, and thank you, Gils, thank you, Alexis, thank you, Rashmi, and Balakrishnan, Venkatesh, Sai Krishna for joining, and thank you all the participants. Have a nice day.
Thank you.
Bye. Thank you.